Okay, do we want to get started? I think so. So, welcome everybody. Thanks for joining our webinar today. I'm Mike Mensch, the Business Development Manager at Princeton Consultants. My colleagues Irv Lustig and Rob Randall will be discussing advanced optimization techniques for complex scheduling. We're going to go for about an hour. We are leaving time for Q&A at the end. There is a Q&A box at the bottom. So post your questions there and we'll try to get to those. We are recording this webinar. And we will send a copy of the slides if you've registered. We'll email them to you. And on that note, that's our housekeeping. I'll turn it over to Irv now.
All right. Thank you, Mike. So as you all know, we're going to talk about advanced optimization techniques for complex scheduling. We're going to cover a number of examples and methods that we've used here at Princeton between Rob and I and our team to solve some pretty complex problems. First, let me say a little bit about Princeton Consultants. Our roots are in information technology and management consulting. We've been around for over 45 years, I think it is now, maybe not that long, but certainly a long time. And we started off in doing the management consulting and realized that computing back in the 80s could help make better decisions, and have now do a lot of work in optimization. We have clients in almost every industry, from large to medium to small. We've been in business 43 years, done a lot of projects, a lot of experience. Our senior staff has been around quite a long time, have our directors, and our mission is really helping clients accelerate their digital transformation. So now let's talk about our services. In the optimization and AI area, we do a number of different things. So I'll start on the right here, advanced analytics team best practices. We talk to firms and try to partner with them and say, how can you help and create an infrastructure, and what are the best practices for building and deploying world-class solutions? In the middle, we have what's called the model review and quality assurance service, where we can review existing models and recommend improvements and make sure that you're using best practices so that you get good speed and quality and robustness. And then the projects that we like the most, and really the examples we'll give you today all come from this, is where we have actually done the complete optimization model lifecycle, starting off with understanding a business problem, transforming it into what would be an optimization solution, implementing that solution, and then making sure it gets deployed and used in the business. So let's talk about scheduling problems. Scheduling is an overloaded word. So we're going to be talking about scheduling problems that have typically have a set of tasks that have either constraints or requirements on when they should start, how long they should be, and when they should end. And each of these tasks are competing for resources. So in general, you have a constraint for every time in your horizon as to how many resources can be used. So if you take an example that you see in the graph here, you've got a set of different tasks that have been scheduled, and over time on the bottom you see how many tasks are kind of active for every day in the schedule. This is a schedule that is spanning over the course of over a year and a half, and each task is scheduled at the granularity of a single day in terms of when it can start and end. So the decision you're making is, when should these tasks start and end, using which resources, and then you can add kinds of constraints that are precedents between tasks, that a certain task must begin or end before another task's. What is the overall resource capacity? How many active tasks can you have at any particular time? You can also have sequence-dependent transition times and a whole host of other constraints that relate to shuffling these tasks and ordering them over time. We also talk about rostering problems. These are also sometimes called scheduling problems. In this case here, you could be determining a schedule for workers. So here we have a bunch of workers on the left, A through T. We have dates of the month, the 1st through the 30th, with the days of the week. The yellows indicate the weekends. And then for each person, we have to determine what shift they're going to work. There's different shifts within each day, the A, M, V, or N. And there may be sequence rules that occur for each of these resources, in this case, the people. Um, but also for each date, you have a minimum and a maximum number of assignments that are needed. And we'll see an example of this later in a way that we've solved this kind of problem. The important thing here is that what makes a rostering problem difficult is that over time, for each person, the kinds of sequences that you can have are are dictated by certain kinds of constraints. This is a little bit different than a slotting problem, and slotting problems are actually a bit easier to solve. In this case, every task is the same length of time, but there's no constraint that exists on the sequence of tasks over time. You notice that this picture here looks similar to the previous one, but in this particular example, there was nearly no requirements of what should happen over time for each one of the people that we're scheduling. So generally, you're just assigning a person into a time slot, maybe into a shift, without any worries about what the sequences are over time. Now, when we're doing scheduling of these types of things, there's different types of objectives and constraints, and you have to think about what's the objective and what's the constraint. And in some sense, what happens is the three components of the tasks and their length of time each one must take, the time that you want to complete the tasks in, and the resources that they're competing for are all pulling and pushing against each other. So if you can fix any one or two of these and optimize the third. So for example, if I have a fixed amount of time and a certain number of resources, the question then is how many tasks can be completed? If I have a certain number of resources and a number of tasks, what's the shortest possible schedule? This is the classic thing called the make span, finding the shortest schedule. A lot of people think that that's the only kind of scheduling problem. And then the third idea is that if you have a given number of tasks and a finite amount of time, how many resources are required to complete that schedule? So you can optimize any one of the three of these if you fix the other two. And so as you're talking, we talk to clients, we try to get a good understanding of which of these components is most important for their scheduling problem. The other aspect of scheduling is what I like to call the scheduling cadence, which is when do you create schedules, when do you publish them, and when do you modify the schedules? So here's an example from a client that we had that on an annual basis, towards the end of the year, they create a schedule for the following year. Every one of the tasks lasts multiple days, and towards the end of the year, around November or so, they publish the schedule for the entire following year for review, and people can give feedback, and maybe they missed a constraint or specified something wrong, and they can create new schedules. But now, as that year unfolds, during the year, every Friday, they go in and modify the schedule. So they collect information that, hey, we thought this task was going to take 8 weeks, it's going to take 9 weeks, or we need an extra person on this task. But what happens at any point in time is that the next 6 weeks of the schedule, there's things that are already in motion to start those tasks. So they freeze that 6 weeks or anything that's currently already started. And then you can optimize any tasks that are scheduled beyond the 6 weeks. And then you publish that new schedule for the remainder of the year every week. So this cadence of doing an initial schedule and then rescheduling on a weekly basis is something that you have to be aware of. Scheduling problems are typically not just done one time, but are redone and are based upon an existing schedule that's already been pre-computed, as well as that schedule that's already in motion for that's already being executed based upon the previous plan. So why scheduling so hard? So a lot of people we often go and use on many of our projects mixed integer programming. The problem is with these problems is that the solution space really gets very large as you increase the number of tasks and the number of resources to schedule because you're making a decision based on an entire time horizon. So if you're doing something like the previous example of deciding when things should start for an entire year, and you're deciding something for every day of the year, there's a lot of decision variables. In addition, there's a lot of symmetry in MIP, which means that there's two schedules that really kind of look the same, and it's hard for the MIP to determine what's different between them when it looks at the linear programming relaxations. In addition, that a lot of solutions can have the same objective value when you look at the linear programming relaxations, making it hard to improve the objective value. And I've mentioned the weak LP relaxation. And so when you add all of this up, you've got to look to see if you can find alternative solution approaches, which is what we're going to spend the rest of the seminar on. So these other approaches might be needed, and we're going to talk about three different types of approaches. For scheduling problems, we'll talk about schedule generation and constraint programming. For rostering problems, we'll talk about reciprocating integer programming, RIP, which is something we created here at Princeton. And for slotting problems, we're not going to talk about them. They're kind of not complex, and our seminar here today is about complex problems. So with that, I'm going to turn things over to Rob, who's going to talk about schedule generation.
Thanks, sir. Um, we're talking about schedule generation today, which we've used on give me permission, right? Or there we go. Okay. So schedule generation approach, the goal of that is to take away the difficulty from the optimization model itself and to push that complexity into a tool that can um, handle the increased difficulties, which we use a rules engine approach often, and some technology to be able to do multi-threading, multi-processing to create many different feasible schedules, and then use the optimization tool just to solve these much simpler problems. So in the example use cases we've had that use a tool like this is fractional airline scheduling, dray trucking, load assignment, and some bulk chemical trucking trailer assignment. And we'll talk about the first and third one here today. Um, so for schedule generation, the algorithm really works in two phases. The first part is to generate a set of schedules that are feasible in the model. For a small problem, you can do this nearly exhaustively. But for larger problems, you use your business knowledge to understand what schedules should be done and what should not be done. The goal will be to prevent them from being generated. Then secondly, you will solve a simplified MIP, in this case, a set partition problem that ensures each asset is only used once, and we only schedule each resource and task one time. So in many of our cases, in the case where we use for this, we use a recursive technique for each asset to add tasks on after to continue adding tasks on. And one of the key pieces about this is it allows for highly parallel processing of the schedule generation. Okay. So as an example of the schedule generation, we'll start with the following 5 flights. And uh, a little data. We have an aircraft. We only have one aircraft we're looking at here just for some simplicity. It landed at 8 p.m. On the 7th. We have one crew, no backup crews. So in a few rules to help us determine what's feasible, the crew can work for 14 consecutive hours and must have a rest period of at least 10 before they can work again. They must start working an hour before the first flight of the day and have an hour between landings, one landing and departure of the next, and then at least 1 hour at the end of the day. And all that must be done within 14 hours. So can we add the first flight to the schedule for the aircraft? And so if we look at it, they landed at 8 p.m. That means they are available at 6 a.m., 10 hours. And so the first flight takes off at 7. We have an hour beforehand and an hour afterhand. So in this case, everything is feasible. So yes, we can add that flight. So we take that one, right? Recursive, we're now trying to add the next flight. Can we add the second flight? And the answer here is no, because there's not enough hour. There's not an hour between them, right? You couldn't land, prep for an hour, and take off. Even though they're in the same place, there's not enough time to do it. So we can't add the second one. Can we add the third one? And the third one was the Miami to Atlanta trip. So now they're not in the same location, right? So now we have geography mismatches. So we need to create a repositioning flight to connect them. You can definitely think of repositioning flights as a form of a sequence-dependent setup if you're thinking about this in a traditional machine scheduling way, right? So you had to finish the first flight. Now you have to move the aircraft to the second flight. So they are all sequence-dependent between where you are and where you're going. However, so now we got the aircraft in the same place, but they can't go back to back because now you can't create a repositioning flight that takes off an hour after this one and gives you an hour before that one. So that one doesn't work. Okay, moving on to the next one. Can we do this? Okay, sure. They're not in the same place. We need a repositioning flight. We can build one now. However, this is where one of the difficulties of traditional scheduling comes with a MIP, right? Is where would you put this repositioning flight? Because you could put it, if you were using constraint programming or MIP and you tried to build a repositioning flight here, you could put it anywhere between 10 a.m., parting between 10 a.m. and arriving by 1 p.m. Anywhere in there is an identical schedule. So in this case, we use the algorithm decides based on some rules of where to put it. There are many different rules you can do, and we often talk to the client about how they would actually schedule this flight in general to meet these needs, to know where to put it, whether you put it as soon as possible, or as late as possible, or somewhere in between. In fact, for one project we did for an airline scheduling company, we determined when to build the repositioning flight based on dynamic backups of aircraft in their schedule. So you might move it. Actually, you might set it for 11:45 because until 10:45 you can use it as a backup flight for another trip. In particular, like this flight, the Newark flight here, right? You could use that aircraft as a backup if there's a delay to the flight. But once it's taken off, now you can move the plane to Boston to take the next flight. So now can we add the fifth flight, the Newark flight here after this one? Clearly not, right? Because it takes off before the Boston flight. You do it there. Can we now instead add it after the first flight? No. Again, for many rules, right? We can't do it because after landing here, you would exceed 2100 on the departure time, so it would be too many hours of flights. So now you can see I just kind of showed by hand how you would generate the schedules, and then we would feed it into a model, which we'll get to shortly. But we're talking about an actual business example here. So we had a client. They were a small mid-sized fractional, and they were started using our basic tool. However, one of the big issues in real life scheduling and real life optimization, right, is actual data. And their inaccuracies in their data were preventing them from being able to use the tool correctly. So they asked us if we could make a slight modification and not use real aircraft, but to give them a set of flights that they could kind of see where they could put them on the existing aircraft that they knew were available. So to implement this, we had to modify our existing model to not use real aircraft, but to use these fake aircraft that basically gave us a placeholder to start. And then we would generate the schedules as normal off of that. But then we would create a positive slack calls to not use an aircraft so that you just didn't use all the aircraft that were perfect, but you tried to put them together. Again, they had other issues, capacity issues. So you add third-party subcontracting, third-party lift, and then we use some technique there to kind of modify and create the tool for that. But so part of this is showing how we took all the complexity out of a scheduling problem, right? So we did all this on, technology-wise and rules engine based, and then there's a very straightforward algorithm or a model to solve, right? We just have the simple variables of X, there's a 0 or 1 if you select it. If S of T is a 1, if tail is not used for select schedule, otherwise 0 or 1 otherwise. And then flights there. And so you can see a very straightforward objective function to maximize profit. And then some very simple constraints, right? So each tail can only be used once. Each flight can only be assigned once. If we want to limit, in the example we were talking about, right, with the strings, we want to only build so many schedules for certain cabin size of aircraft. So we had a constraint that limited that. And then another piece of it is we only want to alter the start time. So we can only alter start time for so many flights in a day to not be what the customer really wanted. So we have a limit on that. Okay, so that's kind of the model for that one. And then a second project we used this on was for some bulk chemical. And it was so this was an interesting one that we did because there are many pieces of bulk chemical trailer optimization. And we kind of went back and forth between the generation and taking feedback from the model here. So we started by scheduling the trailer routes without adding the washing at the end. And we solved it as an LP. And then we took the reduced cost back to that to know where we should use the post wash on them, and then solve it as an LP and an IP. And then we've then used the reduced cost to figure out which of the trailer routes we wanted to try to work the driver assignment sequence generation into. So then you do the same thing there with the driver work assignments. And then you feed it and you keep feeding it through, and then you get the optimal solution for that. In this one, the complete cycle time, and this is actually many years ago. It's actually probably much faster than that now. I don't have any updated data on it, but so it was a 2017 Wagner Prize finalist for excellence in practice of advanced analytics and operations research within forms. But we were able to do a very big problem very quickly because of the iterative approach and the schedule generation versus trying to solve it optimally using MIP. And then I will pass it back to Irv to talk about constraint programming.
Thanks, Rob. So let me now talk about how we use constraint programming and why for certain kinds of scheduling problems. So constraint programming is another alternate technique for MIP. It originated actually in the AI research community back in the 80s. We have a lot of example use cases where we've used this. We're doing a project where we're scheduling patients and workers in clinics. We did another project for scheduling cargo for an airline that's going to do pickup and deliveries. Another project which was to schedule satellite coverage around the Earth. And then the one I mentioned earlier, which was kind of a long-term task scheduling and figuring out a bunch of tasks with competing resources over the course of a year. So what's common about these and what makes constraint programming different is that basically in MIP, you've got linear equations, the variables are either floating, required to be integral, you have to maximize or minimize the linear function over those variables. You generally use branch and bound to solve this. You fix the variable, solve a linear relaxation. The problem is that when you use when you create a MIP formulation for a scheduling problem of this kind, where you have these tasks of different lengths of time and a constraint on every time period, that generally the relaxations are very, very weak and branch and bound doesn't work well. So constraint programming uses a different language to represent the problems, and it generally is very good at finding good solutions very quickly, not necessarily provably optimal, but getting good solutions to certain scheduling problems. So why do we use constraint programming? So one reason is it has a better language for specifying these types of things. So it has this concept of called an interval variable. An interval variable you can think of as having it as a task. And what it has is when should the task start, how long it should be, and when it should end. So there's an implicit constraint that says start plus duration equals end. You can make any of those things variables. Typically, you know the durations, and then the start and end are then implied. And then you have functions that relate these intervals, such as these two intervals cannot overlap in time. All right, that would correspond to a disjunctive constraint in MIP. Or you can have precedence constraints that says task end must end, V1 must end before V2 starts, which is essentially a relationship between the end time of one interval or one task and the begin time of another interval. And there's a whole set of these types of length constraints that are appropriate for representing the idea that you're scheduling tasks over a horizon that are competing for resources. You also can indicate how much of a resource they consume over the time that they're active. There's generally some specialized algorithms using A star, which comes again, it's similar to branch and bound, to look through the state space and find improving solutions. Notice we didn't say optimal here. The idea is to get good solutions quickly. And there's also kind of reasoning that's going on when you have tasks about intervals so that it understands that if you've fixed one interval and said this is when a task should start, that immediately reduces the search space for other intervals that say must come either before or after it or not overlap. There's no linear relaxation here, so you don't have a concept of a weak lower bound, and the good solvers actually have techniques of computing lower bounds in a quick way so that you can actually approach getting optimal solutions. So let's take a look at a small problem where we initially were doing a POC for a client, and we started off by saying, let's try to make it with MIP. In this particular case, we had 33 tasks, and there were 3 resources, and each one of those resources can have 4 tasks assigned to them at one time. So this is actually corresponds to that clinic scheduling problem, and it didn't have anywhere near all the final constraints that are in the application that we've built. But it was to do the POC showing that we could do this kind of scheduling. When we wrote out the MIP for this simple 33 task, 3 resource problem, because we were scheduling at the granularity of every 5 minutes, so over the course of the day, you're going to then have on the order of you know 36 or 360 potential times for each one of the tasks. So we had 134,000 constraints, 15,000 and more variables, all of which are integer, and 15,199 of them were binary. When we try to solve that problem on an M1 Max app using Mac that had all 10 cores using an older version of Gurobi, and the newer version wouldn't make much difference. It took about 89 seconds for it to find a feasible schedule, which was using some heuristics that are built for MIP. And then after 172 seconds, we then knew it had found the optimal solution, but it was still taking a long time to prove whether it was optimal. And in fact, in over a 10-minute time period, it only found these two solutions, the first feasible one and the one that we knew was eventually to be optimal. And it was all being done by the MIP heuristics. Branch and bound was really not making any progress on the problem. So that 172 seconds to get to what we know to be the optimal solution for a relatively small problems that doesn't have a lot of complexity to it is a bit concerning. We then used constraint programming. So you'll notice here that the number of variables is 1,002 and 802 constraints, because now we are not representing a variable that corresponds to saying assigning this variable to a particular time period. The actual time period starts is the part of the solution. And then you'll see that we actually solve that problem in 0.06 seconds. So it was clear that for this kind of task scheduling problem, competing for resources, constraint programming is really the way to go. And so when we see these problems, sometimes they look like job shop scheduling or things where you have tasks of different lengths of time competing for resources. CP really seems to be the best way to go. Now, one thing you can ask is say, well, let me go back a slide here. You'll see that in this particular case, we did get a provable optimal solution using CP Optimizer, the IBM iLog CPLEX CP Optimizer. But is optimality even a requirement? And in fact, a lot of times, what we find even with integer programming is you can wait a long time trying to get approvable optimal solutions. And so you don't want to wait for and it's usually just waiting for the bound to be improved so that you can prove optimality. So we generally say that the client will say, give me the best solution you can find in 5 minutes or 10 minutes. So what we do in constraint programming a lot of times is we do what I call the punting strategy. Basically, we look at how the algorithm is progressing, and then we set a time limit, but we also say if you haven't improved the solution in say 30 seconds, punt and just take the best solution, because we kind of feel like maybe it's searching and searching and searching, and there's no reason to continue to search at all. So we kind of control the search there in order to return good solutions quickly without worrying about the fact that the modern constraint programming optimizers are trying to prove optimality. So now let me talk about a new technique that we created here at Princeton called reciprocating integer programming, and explain how it can be it's something we developed. We actually solved it to solve a packing problem, but it turns out that we can also use the same technique with a certain kinds of scheduling problems that fit into rostering. Okay. And this is actually can be used along with the technique that Rob talked about to generate subproblems. But in this particular case, we used mixed integer programming to do the generation of, say, schedules, if you will, and use mixed integer programming to combine the schedules. So we have two use cases. The first one, which I'll talk about last, was subscription box configuration. This is the one that we actually created RIP for. And then, but I'm going to talk about RIP in the context of nurse rostering. So the way RIP works is that you think about that that you have a whole bunch of patterns of potential schedules of, say, nurses that they can have, like when they can work, what kind of shifts they can have, how the shifts can transition from one day to another, how many weekends they can work, etc. And so what we do is we can actually write out a problem that's a MIP that contains all the possible patterns, but we don't want to generate them all. So we use column generation, where we generate the patterns as needed, and we form what's called a restricted master problem. It's not a true column generation, because what we do is not just add columns, but as we add columns, we may have to add new and variables, we add new constraints. So it's not really branch and price. You can consider it a kind of a price and branch scheme. And we think it's actually maybe better than classical branch and price, because we're taking advantage of the power of the MIP solver with its pre-solve and different heuristics, etc., which you typically have to turn off when you're doing things like branch and price. So here's an example of this nurse rostering problem. You'll note that there's there's weekends that we have to worry about, and there's different shift types. In this case, there were 4 different shift types. And what we have to do is we have the nurses that go up and down. For each nurse, we have to generate a schedule. And let's look at the kinds of constraints that exist in this kind of problem. And this is from a standard set of test instances that are out there. So there's particular hard constraints that you can't assign an employee more than one shift in a day. There's some restrictions on which shifts can follow different shifts. So, for example, if you have a night shift on one day, you don't want the day shift on the next day. There's requirements on for each employee, what is the maximum number of a shift of each type? So you may have a limit for the month of how many night shifts or how many day shifts, etc. Each shift has a certain total time, a number of minutes, and you want to look over the course of the month. What is the maximum time total minutes that can be assigned and the minimum total minutes? And then you also have the maximum consecutive shifts. So basically, you look at a consecutive set of shifts and then you have to have a day off, or a minimum number of shifts that you must work before you get a day off. So you don't want to have somebody have a day off, work a day, and then have a day off, and then a minimum number of consecutive days off. And then there's a maximum number of weekends that can be worked. And there's also requests that certain employees or the nurses cannot work on specific days. So these are all things that come from these scheduling benchmarks as constraints, and you can specify with data what are the specific data that come into play. There's also some soft constraints. So you have a employee that can say, hey, I would like to work this shift on this day or not work this shift on this day, but it's a request, it's not a requirement. And then also you have a cover, which is a requirement that says on each day, how many shifts, how many people need to be assigned to each shift. And so these three are considered soft constraint violations. So again, this is taken from this nurse rostering example. It doesn't necessarily represent what happens in the real world, but we wanted to use this and say, out of these 24 instances, how well could we do? So in RIP, the way this works is we have two MIPs. We have a MIP that generates the patterns for schedules of nurses. So if I go back a slide, these hard constraints that you see here, the first set of constraints are all related to, except for the first one, which is about, actually it is for the first one. This is basically, think of it like the strings that Rob was talking about. If I look at a month's worth of a schedule for a nurse, all of these things if I'm looking at a particular nurse, I can generate patterns that correspond to these shifts. And then the question is, how do I combine those patterns so that I deal with the cover constraints, which are how many people need to work on each day? So in the restricted master problem, we worry about that. In the pattern generation, we're generating a lot of patterns that will be valid schedules for individual nurses. And what we first do is we solve an LP that makes sure that we can have a feasible problem with respect to linear programming of the restricted master problem. And then we have a way of generating duals from a MIP as well as from LP that helps influence the new patterns that need to be generated. So these go back and forth and back and forth, and we keep going until we feel like we can't generate any more patterns that will improve the solution. So when we applied this to those standard set of examples, we actually first developed RIP for Birchbox, which I'll talk about in a moment. But when we applied it to the nurse rostering, we actually were able to solve the first 14 instances to optimality pretty quickly. And then actually for three other instances, we found new solutions for instance number 15. And then for one of the other instances, 19, we improved the lower bound. And for instance 20, we were able to actually prove to optimality. We were the first that were able to do that. So we were pretty excited that this RIP technique that we developed for Birchbox could be applied in the nurse rostering context. And we're looking for other places where we may be able to do the same in scheduling problems. It's worth having this quote here from David Bendis, who we worked with at Birchbox. You can see here that we basically took what was their original MIP and taking around 48 hours to solve. And in general, they were getting solve times using our RIP algorithm in about 15 minutes. This allows them to try lots and lots of different scenarios and different ways of configuring products into boxes. We have a this project was also a finalist in the Wagner Prize competition in 2020. And there's a published paper about this, as well as the one that Rob talked about with the bulk tanker scheduling that you can get from the Informs Journal on Applied Analytics. And so you can get all the details of those algorithms there and how they work. So let me conclude with the following. You have to remember that not all scheduling problems are created equal. We've talked about the kinds of problems that Rob has, which are in flight scheduling, bulk trailer scheduling. We're scheduling things in space and time, and we have competing resources in aircraft. You've got to worry about aircraft, and you've got to worry about crews. In the bulk trailer scheduling, you have to worry about the trailers, and you have to worry about the drivers. So you've seen that those are different from just the more complex task scheduling problems of scheduling things over time that are competing for resources, as well as rostering problems where you're scheduling people to work on days, but there's requirements on how things have to occur over days. So generally, when most of these conditions that you see here occur, that you have tasks that differ in the length of time, you have a long time horizon, during every unit of time, the tasks are competing for limited resources, and there's precedence constraints, constraint programming will work really well. On the other hand, when you start having things where the rules of how you're generating sequences of tasks are complex, you may have to use some form of column generation with MIP, and that as an example so that the individual schedules fit together, like in the flight scheduling, we use a rules-based approach to generate sequences, or in rostering, we can actually use MIP to generate the sequences. But if you're just assigning tasks to time slots and say, this task has to go here and this task has to go there, or you have smaller time horizons, and the constraints across time are not too complex, you can get by with MIP models. So we've become pretty adept at looking at different kinds of scheduling problems and having some real insight as to which of these techniques we should use first. So with that, I'll move over to and say thank you for coming, and I hope you enjoyed the webinar. And with that, I'll turn things over to Mike to process any of the questions we've had.
All right, thanks, Irv and Rob. First question, Irv, what you were just talking about there, is there a general problem characteristic to identify where RIP can be applied? So you were talking about some general characteristics for the various
So
alternative techniques.
yeah, so what we've seen is if it's easy to generate the patterns in via MIP, that's where we like to use RIP. So if you take the examples that Rob gave, where you're trying to find, say, a sequence of flights that meets certain independent times, and it's happening, and you're worried about there's a spatial component, it's kind of easier to write a generator that, because it's hard to state that problem as a MIP. But in the case of the rostering problems, you're just looking for like these strings, and it's kind of easy to have MIP. If I go back to that picture, if you think here, what we have to do is for each different nurses, we have to generate these strings, and representing the constraints for these strings is pretty easy because the time horizon is only 30 days. So in the case of when we were doing the Birchbox, we were generating patterns of products that would fit into boxes. So what would happen is you would have about a choice of, say, 100 or 120 products, and you had to pick a subset of 6 of them that met certain constraints that would fit into a box. So each one of those variables is a binary variable. The MIP solved very, very quick, and that allowed us to quickly generate patterns. So it was kind of easier to write a MIP to generate the patterns than it would have been to write a rules-based approach. Conversely, in the examples that Rob gave, it's the reverse. It's really hard to write a MIP to generate the patterns. And then it's better to just use some form of rules-based generation. But fundamentally at the top, you're solving a MIP to actually combine everything together. I don't know if Rob, you want to add anything to that?
No, I think you handled that pretty well. I mean, yeah, it's the key part difference between constraint programming and schedule generation, or between MIP and schedule generation, is being how complex is it to create the schedule.
All right, next question, Mike.
Okay. Yeah. Um, Thank you very much for the webinar. Are there any repositories available for these methods that you recommend? Um, I guess we can package up, Irvin, Rob, articles that have been published about a couple of these case studies, and blog posts. But other than that, what would you recommend in terms of repositories?
Well, in the case of both the flight scheduling as well as RIP, we consider that our intellectual property. Even though we've written publications, so we're not willing to give out the code because we're hoping to be able to use it with some of our other clients. But the paper is out there. The papers are out there that describe exactly what's there. So as Mike mentioned, we can send copies of the paper. In the case of constraint programming, um, we've used two commercial products to solve scheduling problems. One is IBM iLog Cplex, which has a feature called CP Optimizer, that was probably the first real robust commercial product for using constraint programming and applying it to scheduling problems. And there's a lot of good tutorials online. And from IBM, you can get a free trial edition that limits the size of problems you can solve. And there's some good tutorials online for that. And then in addition, we've also used Google OR tools. They have a solver called CP-SAT, which is a constraint programming SAT/MIP solver. It's kind of all in one, but it has a very similar language for specifying the scheduling problems. And they have some minimal tutorials that explain. That's a complete open source package that you can go and download and use to your heart's content for solving problems. That comes from Google. So those are in constraint programming. There's more free stuff. In the other things, you have to read our papers.
And we should add, in keeping with our agnostic kind of stance in the world, Callus is a CP solver owned by FICO. So that would be a potential resource on the CP side as well. Other questions, here's some more coming in. Uh, are there any best practices from a solution development standpoint, modeling, or tooling, that helps to iterate between MIP and CP seamlessly?
That's
Yeah.
tough. I mean, there's two types of iterations there, right? Because sometimes what we end up
Yeah.
doing is, as we're solving a problem, we might actually build a MIP model and build a CP model and try to learn from, as we're doing each one, which is the best way to go. Because there's a fuzzy boundary between when MIP is okay and when CP is okay.
Hmm.
And so we kind of use our intuition as trying to do that. There's a second aspect, which is you can also use column generation approaches where instead of using a MIP to generate the patterns like we do with RIP,
Yeah.
you actually use CP to
CP.
generate the patterns. And there's actually um, uh, a long ago when I was working for iLog, there was this ACC basketball scheduling problem that Mike Trick and George Nemhauser wrote a paper on in the late 90s in operations research that they solved with MIP. And then we developed an example using OPL that showed how to use MIP, but have to use CP to generate potential schedules. So it, there's an art and a science to it. A lot of it is just based on intuition. I think it's kind of hard. You know, what we like to do is find tools where we can use the same language for development. So we pretty much do everything in Python these days. So for example, um, in the case of the Birchbox and the nurse rostering, since we were doing MIP, we could write everything in Python and we did everything with Gurobi there. In the case of like the constraint programming that we've done with both Cplex as well as OR tools, we'd again do everything in Python. If we're trying to combine the two, OR tools is one option because you have Python interface for both, and so is Cplex because it has both. And so that way, if we keep the modeling layers in Python, then it makes it easier for us to manage and do any iterating between the two.
Okay. Um, how do you or how would you handle the rescheduling problem where, for example, 5 weeks are or should be frozen and weeks beyond should stay as stable or close to the previously generated schedule as possible by some criteria? But
So
that's a tough
that's a
one.
good question.
That's good.
Yeah, so we actually did that on our
Hmm.
on this project that I mentioned, where we reschedule every week. So what we do is we freeze the first 6 weeks, and then um, we reschedule everything else, and then based upon the main objective, which is keep the schedule as short as possible. And then we do a second objective, which is minimize the number of changes. And so number of changes could be either measured as how many of the tasks changed when they were starting and ending, and or um, once you've done that, you can also look at minimizing the amount of time that they change, or you can just do the former and not the latter. So, and Rob, we've done that also with the
Yeah,
clinic
with the
scheduling problem.
plan scheduling, we do the exact same thing. We have a secondary objective where we limit how many things can change, both in terms of what resources are being used, as well as what is whether or not the start time of the appointment changed.
So we generally like to have the main objective, and then we use a secondary objective. It's a multi-objective problem where we solve the second problem. We've solved the first problem. We have an objective for that. Go to the second objective of minimizing some measure of change in the schedule and minimizing that, subject to not making the first objective worse.
In the case of the airline scheduling one, we also not we actually sometimes we will create a constraint instead of an objective saying what are the maximum number of changes you're allowed to have of a certain type. Just because sometimes you may not create by creating other changes, you may not be really limiting the change to be feasible. It may still exceed the amount they want with a primary objective in this case, not just a secondary objective.
Okay. Apart from articles and blog posts, and we will send links. We've been asked that, but are there any good resources you recommend for someone who's just getting started in this area?
Well, so in constraint programming, there are um, some good tutorials actually that IBM has put out about
Yeah.
how to use how to use, I mean, in their case, Cplex CP Optimizer for scheduling problems. So you can find that. They have a library called Do Cplex, D-O Cplex. And if you search for that and you look at their examples and tutorials, you'll see some really good things that can help you understand on the constraint programming. And there's a lot of examples. There's some other people who've written some different things and ideas for how to help in constraint programming.
Well,
The
including
first,
Irv. Irv wrote a paper on comparing MIP and constraint programming many years ago.
right, and that's actually open access. So there's a paper I wrote in around the year 2000, that's about program does not equal program. Constraint programming and its relationship to math programming is also a good way to learn about constraint programming if you understand math programming. In terms of the kind of column generation techniques that Rob and I have spoken about, the 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 schedule generation or in RIP, those actually have a basis in general column generation techniques. There are books that have been written about column generation that can help you learn how to think about it. It's pretty advanced from an optimization standpoint. I know there's a book out there, and I can look it up after the seminar that was written by I think it's by Jacques Desrosiers. I'm probably saying his name wrong in Canada. Um, they've written books on column generation, and not that I've read it, but I know there's a lot of interesting stuff in there. Probably my experience from it was learning about Danzig-Wolf decomposition back in grad school, and actually having done research in it when I was a professor at Princeton. So it's an art and
Yep.
at these
Bolster.
techniques over
Oh,
time.
Okay, there we are. Uh, can I just add that at a more fundamental level, what can we tell the audience if anyone is they're not that advanced, just in terms of informs, because the annual meeting is coming up, so a number of us will be there out in Seattle. Well, if someone wants to get started and get access, what should they do through informs? Where, by the way, your paper that you referenced from the year 2000 exists, but anything else in terms of um, education or resources.
Not sure Informs has anything specifically beyond all the large set of publications in the journals that they've had.
Okay.
Like the paper I mentioned, we happen to back in the iLog days, we actually paid for that paper to remain free to all. So that paper is wide open. But there's a lot of research and papers that that are out there that are published by Informs. Not educationally, I don't think anybody really does anything. There's a lot of people out in the academic community who work in this area that have published stuff, and that's kind of you have to find the right things to kind of learn about it. I do think that book I mentioned, which I have to look up, will probably be a good source if you want to learn about column generation techniques.
Okay. We have one more question. We do have time. If you want to post in the Q&A, please feel free. Last question so far. In supply chain, there are many problems that are solved using optimization. Is there a set of standard methods that can be used to solve inventory, production, schedule, and route optimization problems?
Want
I
to
mean,
take
these
that
are
one,
also,
Rob?
I mean, these are often multi-level scheduling problems, right? I mean, so there are many techniques that exist in papers and otherwise that can be used. Often in practice, we often find that trying to solve them all at once becomes very difficult and hard to um, explain the answers to clients and to the people who are actually implementing them. So often it's better to decompose them into uh, multiple pieces, and then you get a lot of things like production scheduling and route optimization. That there are other techniques, and you can iterate on schedules in kind of the same methodology we were talking about in RIP, where you can solve one problem, feed it, or in the also in the bulk chemicals algorithmic approach we use, where you can create multiple solutions to one level of the problem, feed it into the next level, and then create feedback loop to go back and make sure you're finding really good solutions. That helped, I hope.
Yeah. Okay. All right. Well, we've gone through the questions. We were asked by a number of folks for links, and so we'll put together a good list, help get started. And of course, feel free when we send that email if you'd like to discuss these issues further with Irvin, Rob. We welcome that. We always want to uh, uh, have conversations about various challenges and initiatives. Um, and so on that note, we thank you again for coming. And I'm just seeing if somebody wrote thank you for the presentation. Well, our pleasure. Thanks. Have a great day, and we'll be looking forward to talking again soon. Take care.
Thanks, guys.
Bye bye.